The intermediate value theorem is the first major theorem we're going to look at. But before we do that, just a little more notes on continuity. We say that functions can be continuous even if their limits don't really exist. And that's when we talk about functions with like endpoints. So for example, just the square root of x is a function that looks like this. And you notice that right here at the origin, the function does not have a limit coming from the left. And yet we still want to consider our function, our square root function, to be continuous at 0, even though there is no limit at the left. So what we do is we define continuity for those types of points in a very special way. We say that a function is upper semi-continuous or right-hand continuous at a value if and only if the right-hand limit exists, the function value exists, and the right-hand limit equals the function value. So that would be an example of like the square root function where, I don't know why it's doing this. The square root function, notice that the right-hand limit as we approach 0 is 0. The function exists at 0, it is 0, and since 0 equals 0, we're good. This is to prevent a scenario where, for example, we have some kind of function like open circle, and then the point over here. Now, if I approach 0 from the right, this function is approaching some positive number, but at that x value, the function has a negative value. So we would say this is not continuous at its left endpoint because the function kind of goes up, 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 and then jumps. But if we actually filled in this hole, we would want to say, yeah, it's continuous, even though the left-hand limit doesn't exist. The same is true in the other direction, lower semi-continuous or left-hand continuous, if I can approach it from the left. And then we say a function is continuous on a closed interval if and only if it's continuous on the open interval. So everywhere in the open interval, the limit equals the function. And then we're upper semi-continuous at A or right-hand continuous at A and left-hand continuous at B. So once again, here is an example. This is the square root of x function. So let's see. As x approaches A of any value between 0 and 4, not including 0 and 4, we can just plug in. Our function is continuous there. Square root of 1 is 1, square root of 2 is square root of 2. The limit and the function values are equal, and I hope that's clear. As long as I'm not approaching 0, everything can just be plugged in. If we look at the right limit, the right-hand limit as x approaches 0, we see that that is in fact equal to the square root of 0, which is 0. So we are right-hand continuous at the left endpoint. And then we have to be left-hand continuous at the right endpoint. Well, the limit as x approaches 4 from the left is equal to the square root of 4, which is equal to 2. And the square root of 4, it does happen to be 2. So we are continuous on the open interval. The right-hand limit at 0 equals 0. And the left-handed limit at 4 equals 2, which is the square root of 4. So there we are, in fact, good. G of x is continuous on the closed interval from 0 to 6 because, if we look at this, as x approaches any value on 0 to 6, not including the endpoints, well, if I'm going from 0 to 6, then I am in this function because I'm in between 0 and 6. So the limit there would be 1. And the function value for any of those would also be 1. So the limit equals the function value there. As I approach 0 from the right, that's equal to 1. And that's equal to f of 0, because when I plug in 0, I get 1. And if I approach 6 from the left, that's the right endpoint, I get 1. And that is equal to the function value at 6. So we say that this function is continuous on the interval from 0 to 6. And if you actually graph this from 0 to 6, well, just from 0 to 6, you notice that it's this line up here, which is continuous. If I were to try and go from -6 to 0, I would not be continuous. Or, for example, -4 to 0. And here's the reason why. Notice what happens if I try to go from -4 to 0. If you graph this, it's kind of clear from the graph that this is not a continuous function. Because even though this function is continuous on the open interval from 0 to -4, and even though at -4, this function is right-hand continuous. At 0, the function is not left-hand continuous. Why? Well, the limit as x approaches 0 from the left, if I take the limit as x approaches 0 from the left, I'm using this guy, because I'm never actually at 0, which is -1. But the function value at 0 is 1, and -1 doesn't equal 1. In other words, this hole isn't filled in. So this function is not continuous on that closed interval. So that's not something you need to know for the AP exam, but it's just something to kind of complete our discussion of continuous functions, because continuity does play a huge role in various theorems and properties. So this way we can talk about continuous functions that have endpoints. So this is the big guy right here. This says the intermediate value theorem. IVT stands for intermediate value theorem. It says if f of x is a continuous function on the closed interval from a to b, and capital K is any number between the function value at a and the function value at b. That is to say, K is either bigger than f of a and less than f of b, or bigger than f of b and less than f of a, or equal to. Then there exists a number c in the interval from a to b, comma, such that f of c equals k. And you go, what the heck does this say? So let me give you a real world example. Let's pretend that on January 1st of 2020, I weighed 300 pounds. I know, hard to believe, but let's pretend that on January 1st, 2020, I weighed 300 pounds. And then let's say on December 31st, right before midnight of 2020, I weigh 150 pounds. So I weigh 300 pounds on January 1st, and I weigh 150 pounds on December 31st. And if I'm graphing this, then this could be like January 1st, and this would be December 31st. That would be like time of 2020. The intermediate value theorem says, if you give me any weight between 150 pounds and 300 pounds, any weight at all, you are guaranteed to find at least one date between January 1st and December 31st when I weighed that exact amount. The capital K would be the weight in between 150 and 300. And then because it's in between 150 and 300, that guarantees that there is a date, a C, between January 1st and December 31st that I weighed that much. And the reason for that is because weight loss and weight gain is a continuous function. You can't teleport weight away unless you chop off a limb, and don't do that. Losing weight is a continuous thing. You lose it continuously. You can't go from 300 pounds to 200 pounds without hitting every number in between. So what this is saying is, according to my diet, maybe my weight went like this. And then you give me any K, any Y value, it's going to correspond to an X value in this interval from J1 to D31. Or perhaps I was really bad at the beginning of the year. And then afterwards, my weight started going down, and toward the end of the year, I went up again. Well, the intermediate value theorem only talks about K values between 300 and 150. So given any K value between 300 and 150, any Y value between these two red lines, there is going to exist some X value in between J1 and D31. And sure enough, give me any value between 150 and 300 on the y-axis, and you're going to hit some value in between J1 and D31 on the x-axis. It's even smaller than that interval, but that interval is in fact from J1 to D31. So that's basically the idea behind the intermediate value theorem. So to do this more generally, if we have any continuous function, I'll make my function blue. Here's my continuous function. Woo, continuous. And then it's got a couple of these weird points, and then there we go. Okay. Actually, that's a little too complicated. Let's make this a little simpler, just for the sake of it. Go up, down, come down like this, and there we go. Okay. And then we pick an interval. So I'll go from A. Let's say A is over here, and we'll go to B. Let's say B is over here. So what is this saying? You can pick any Y value that's in between f of A, here's f of A, and f of B, here's f of B. So pick any Y value in here. There is guaranteed to be an X value that is going to be in between A and B on this black line. In other words, there will be an X value somewhere on this yellow line if you give me a Y value somewhere in this purple line. So yeah, give me a Y value in this purple line. Okay, here's a Y value in this purple line. Dun, 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 dun. There's the corresponding C, the X value on the yellow line. All right, give me a different Y value in between these. Okay, what about this one? Okay, well, I go this way and nope, that X value is not in the interval. But I go this way and sure enough, this X value is on the yellow line. And that's all the intermediate value theorem says. It basically says you can't lose weight in an interval without at some point in that interval weighing every single value between your starting weight and your ending weight. It kind of makes sense, but it has to be stated this way because mathematics has to be exact, and this is rigorous and exact, as weird as it looks. So how can we use this? What do we use this for? Well, one of the things that the intermediate value theorem is used for is to prove that certain polynomials have roots. One of the biggest deals you're going to see this year is that we like solving equations by setting them equal to 0. And we'll get to that a little bit later in the year, but it's imperative that we are able to do that. And so it helps to know if there in fact even is a solution. If I'm trying to look for a solution and it doesn't exist, well, I'm on a wild goose chase. So it first helps to check to see, is there in fact a solution? So we're going to use the intermediate value theorem to show that this has a root on the interval from 0 to 1. It's polynomial. So if you remember from last year, we could try actually finding the root. We could look at the rational root theorem, in which case 1 and -1 would be possibilities, 1/3 and -1/3 would be possibilities. We could use Descartes' law of signs to try and figure out, let's see, there are 1, 2 sign changes, so there would be 2 or 0 positive real roots. Same thing, there would also be 2 or 0 negative real roots. So we could do all that. But if the rational root theorem didn't work, I wouldn't know where to look for the irrational roots. So we're going to use the intermediate value theorem to show that there is, in fact, a root of this function on the interval from 0 to 1. So here's how this goes, okay? First, we need to know if this is a continuous function. Well, this is polynomial. All polynomials are continuous. We can take that as fact. We could prove it. We don't have the definitions perfectly to prove it, but we said, if you remember, I think Aniket said, for polynomials, the limit as x approaches a of p of x is equal to p of a. So we didn't prove it, but we kind of took that as fact. It is provable, though. We just don't have the math to do it. So we'll take that as axiomatic, that polynomials are continuous. So what else do we need? So we have continuous. We need it to be continuous on a closed interval AB. So our closed interval is going to be 0 to 1. Okay, so this is in fact continuous on 0 to 1. What else do we need? We need a k in between f of a and f of b. So it helps to find f of a and f of b. So let's see. Let's find f of a, f of 0, and that's just 1. And now let's find f of b, f of 1, and that's 3 minus 5 is -2 plus 1 is -1. Okay, and I hope you notice something. This function goes from positive to negative. And this is basically the game. If we were to graph this, for some reason the right side of the board is not working well. If we were to graph this function, f of 0 is 1, f of 1 is -1, and we know this function is continuous, well, even if this function goes all the way up, it eventually has to come down and intersect the x-axis. What that means is, because our function is continuous, and because 0 is in between 1 and -1, f of x has to have a root there. This graph can't just go up and then magically teleport down here and keep coming up. It could go up and come down, or it could go down like this. In fact, it could have more than one root. Maybe it goes up, maybe it goes up, comes down, goes up, comes down. I don't know what this looks like. Maybe it goes like this a little bit. I don't know. The point is, I can't get to that top point. I can't start at this top point and go to this bottom point without crossing the x-axis. And that's the idea. So the intermediate value theorem only proves existence. And so this is going to feel a little bit hollow, but this is how it works. So since f of x is continuous on the interval from 0 to 1, because f of x is polynomial, and that's the first condition we need. So we needed f of x to be continuous on this closed interval. And now we need some number k to be between f of a and f of b. Well, we have that. And our k is going to be 0. Since k is in between, our 0 is in between f of 1 and f of 0. F of 1 was -1. F of 0 is 1. Well, it's a theorem. If the first part of the theorem is true, since the whole theorem is true, the second part has to be true. So we have a continuous function on a closed interval, and we have that 0 is in between the function values at the endpoints. Then we can conclude there must exist a number c in the interval such that f of c is k. By the intermediate value theorem, there exists a number c in the interval from 0 to 1. This just falls out because we have the hypotheses. We have the beginning parts are true, so the conclusion has to be true, such that f of c equals k. And in this case, our k was 0. So because our function is continuous on this closed interval, and because 0 lies in between the function values of the endpoints, the intermediate value theorem, when we use it, just says, okay, that means there exists a number where our function equals 0 in this interval. So there is, in fact, a root in here. That's all that the intermediate value theorem says. It doesn't tell us how to find it. It just guarantees it's there. And again, that's helpful because now I know how to look for it. And if the rational root theorem doesn't work, maybe I have other tools. And later in the year, time permitting, we will look at other tools for finding roots. So here's another example. Last one. Use the intermediate value theorem to prove the following statement. If f is a continuous function on the closed interval from 0 to 2, where f of 0 is greater than 0, this didn't come out very well, and f of 2 is less than 4, then there is some number c in the interval 0 to 2 which satisfies f of c equals c squared is what it says. So what do we need here? Well, we already have a continuous function. We're told that f is continuous on the interval from 0 to 2. And we're told that f of 0 is greater than 0 and f of 2 is less than 4. Then there is some number c in the interval from 0 to 2 which satisfies this f of c equals c squared. In other words, when I plug in the number, out comes the x squared version. So we have to figure out how to solve this. So this is one of the harder problems and not something you're going to have to solve, but I'm going to show you anyway just so you get an idea of how powerful this is. So most of the time when we're dealing with the intermediate value theorem, we're trying to find roots. So I want to find a root. So I have this f of c equals c squared. That's not a root. But what I can do here, this is the same thing as saying that 0, if I subtract the c squared from both sides, would be f of c minus c squared. So now I have a function. I want to find a c such that this function, f of x minus x squared, equals 0. So here's the trick for this. And you'll see it when we do some more problems in class, but this is above and beyond what you need to know. So if you don't completely understand it, that is completely okay. I'm just showing it to you for the sake of completeness. Let's let g of x equal f of x minus x squared. And I need to show that g of x will equal 0 at some point. So how do I do that? Well, I'm going to examine the values of g of x at the endpoints of this interval. So let's see. G of 0 is equal to f of 0 minus 0 squared. Well, that's just f of 0. And we are told that f of 0 is greater than 0. Okay, cool. Then I will examine g of 2. G of 2 is equal to f of 2 minus 2 squared, which is f of 2 minus 4. Well, we are told that f of 2 is less than 4. So if f of 2 is less than 4, then f of 2 minus 4 will be less than 4 minus 4, which is 0. So in other words, we have from this that g of 2 is less than 0. And we have that g of 0 is greater than 0. And on top of that, we have that f is a continuous function. Well, if f is continuous and x squared is continuous, well, the difference of continuous functions is continuous. This was on your theorem sheet from yesterday. The sum, difference, product, and quotient of continuous functions is continuous. So here we go. It's a matter of just writing it out now. I'll do it in red. Since g of x equals f of x minus x squared is a continuous function on the interval from 0 to 2, because g of x is the difference of two, I'm going to abbreviate, continuous functions. And we showed that g of 0 is greater than 0 and g of 2 is less than 0. So g of 2 is less than 0 is less than g of 0. Well, I have a continuous function on a closed interval, and I have that 0 is in between the function values at the endpoints of that interval. So by the intermediate value theorem, there exists a number, I don't know what it is, but there exists a number, we'll call it C, in the interval from 0 to 2, such that g of c equals 0. Well, what does that mean? Well, g of c equaling 0 is the same thing as saying f of c minus c squared equals 0. Or what we wanted to prove, f of c equals c squared. And technically these are proofs, so yeah, I probably should, when I am finished with them, give it the old QED. You don't have to, and the AP exam won't expect you to, but yeah, since these are proofs after all, we should probably give it the old QED. And that is the intermediate value theorem. You really don't have to understand the second problem, example 5, that much. We can go over it more in detail, but the point is that you notice I can reduce this problem to just finding whether or not a function has a root. And that's easy. We want to know if a function is equal to 0. So we ask, is the function positive someplace? Is the function negative someplace else? And is the function continuous? Because, once again, if you have a function that is positive someplace and negative someplace else, and the function's continuous, these 2 points have to connect. And the only way for them to connect is by going through the x-axis. If you remember last year when we were graphing rational functions toward the middle of the year, this is one of the ways we were able to guess what our graphs look like. If you had like an intercept here, and then there were no intercepts on this side, then you knew, okay, the function would come up like this maybe. And then on this side, you knew that the function didn't, if I had like an asymptote here, for whatever, however, you knew that the function couldn't be down this way because there was no other point that it went through. Well, this is the same basic idea. This is saying in order for me to go through this x-axis, I have to be continuous and I have to be positive somewhere and negative somewhere. So the underlying concept is the same. And that, ladies and gentlemen, is the intermediate value theorem. And we will do some practice problems in class tomorrow. You can work in groups, or maybe we'll do them together because these are a little tricky. You can also read the textbook, and I'll put the pages up. It's just a few pages. And yeah, that's it. So enjoy, and thanks again for watching. Bye-bye.